Hi everybody, welcome to Strong Induction with me. Same idea as last time. We want to have our base case. We want to get that, we're going to make an assumption and prove that the next case is always true. That all still works. We've still got like domino effect. If you knock over the first one, you get all the other cases. But strong induction requires a little bit something extra. He's going to rely on all the previous results instead of just the nth one. So when we do our steps for strong induction, we're still going to do our base case. We may or may not have multiple base cases. We will have an example. And then we have our inductive step, but instead of just saying assume n is true, we're going to assume it's always true for the P1, for the P2, P3. All of them were true. And then we're going to use that to get that Pn plus 1 is also true. So I guess strong induction is strong because it comes with friends. I don't know. Okay, the trick is realizing when you're going to use strong induction. A lot of the time, it's going to become obvious during the argument. And so I'm going to start each of these arguments and then go, oh, I need a little bit more than just my normal assumption. And I'm going to back up and be like, nope, we're going to assume this because otherwise my argument's not going to work. Okay. First example, very serious example. We're going to talk about chocolate. We have a chocolate bar and it has a bunch of pieces. We're going to say n many. And it's going to require n minus 1 breaks to separate it into its n pieces. So notice it didn't say anything about how we're separating them. It's just going to take n minus 1 breaks. So if you go row by row, or if you always break it in half, same number of breaks. There's no like efficient way to do that, which is kind of interesting. Let's see if we can prove this. So base case, chocolate bar has to have at least one piece. So n equals 1. That's as small as we can get. So then it requires no breaks, right? 1 minus 1 equals 0 breaks. Because it's one piece. You don't break that up. Okay. Checks out. Now it's time for our inductive step. You're like, but Gracie, there's no formula. How do you argue this? We can still argue this. Let's think for a moment. Suppose we have n equals 6. 6 is a nice number. So then we could have a bar. It's broken up 6 pieces. And we could do a break like this. Then we get, oops, there we go. A piece of 4 and a piece with 2. Yes. So notice we broke it into 2 separate pieces. These are smaller than the original, but not necessarily by 1. Like this piece is smaller by 2, this one's smaller by 4. So we're not just going down, we're not breaking off one piece at a time. Nothing said that I had to, or let's finish this one up. I could break this piece and this piece like that. And then I could also do another break for here and a break for here. So that's going to be 1, 2, 3, 4, 5. All right, that's n minus 1. That's cool. I didn't have to go about breaking it that way. Let's try breaking it up a different way. Maybe my first break was down the middle to make it a half, which only a mad person would break up a chocolate bar like this, I'm just saying. So now we've got 1, 2, 3, 1, 2, 3, like that. So now we're going to do 1, 2, 3, 4 more. So 1, 2, 3, 4, 5 breaks again. So a totally different strategy to breaking up this candy bar took 5 again. Okay. So I feel convinced that this is probably true, but now we have to actually prove it's true. We have to deal with unpredictable breaking. But what we do know is that no matter how we break it, the resulting pieces are going to be smaller than what we had before. But we don't know how small. Okay. Let's see. Do I want to keep some of this? I think I want to keep some of this. Let's keep maybe a little bit. Okay. I'm going to keep him somewhere safe. There we go. Go be over there. So now in deductive step, I'm going to say, assume, how did I write this? Assume the condition holds for n. Now we need to show that it works for n plus 1. So what I'm going to do is consider a chocolate bar with n plus 1 pieces. So then when it's arbitrarily broken we get 2 chunks. What can we say about chunk 1? Well, it has a certain number of pieces in it. We don't know how many. So we're going to say it has k pieces. And what can we say about k? Well, it has to be at least 1. But then chunk 2 needs at least 1 piece, and so there can't be any more than n pieces, otherwise he'd have all the pieces. So it's got k pieces, k is going to be somewhere between 1 and n. Chunk 2, what I don't want to say is I don't want to say he has j pieces. I don't want to invent a new variable. I want to use what I already have. So he's going to have this, like in total, they have to add up to n plus 1 pieces. So n plus 1 minus k pieces for chunk 2, right? So now if we add these guys up, we get n plus 1 pieces in total. There we go. So that's what I can do. So now we've got our chocolate bar broken up into pieces. Now I want to say something about how this is going to break. So we can say that he's going to break in k minus 1 pieces. Or, let's say he requires k minus 1 breaks to break into its k pieces. But wait. That wasn't what I assumed. I assumed that it only held for n. So this is when you go back and you're just like, oh, not n. I want it to be true for all n. I'll be careful in the natural numbers, starting at 1, including 2, and up to n. So now I have all of those numbers. K is one of those numbers. It is somewhere below n. And so I get the condition holds for K. So now I'm okay to write this. And then same for this. We've got it's minus at least 1, because K is at least 1, which means at most we have n chunks or n pieces in chunk 2. So that means we are also sitting somewhere in here. And so he's going to require n plus 1 minus K minus 1 breaks to get down to his individual pieces. Okay, so in total, if we add up all these breaks, we've got, let's see, so that simplifies to just n minus K down here. And then plus K minus 1. Did I do this right? Oh, I'm missing a break. Consider a chocolate bar with n plus 1 pieces. When it's arbitrarily broken, we get 2 chunks. So that's 1 more break. So that's the initial break to get chunk 1 and chunk 2. So in total, we have this plus this many breaks. We know that the chunks will break correctly because that was our assumption. When we add this up, we get that this equals n. So this works. So why do I get to assume that all of these works is probably like the biggest question. Because if we were to start at n equals 1, then that would be the only condition. So then we would have exactly one condition, and that would be n equals 1. And so then we get to have P1 implies P2. And that's safe. So I said P1 is true, therefore modus ponens, P2 is true. And then you just keep repeating this. Be like, okay, so now I can use that P1 and P2 are true. And now I can go after I need to go after P3. And then once I can prove that one, then I also get that P3 is true. And so I can just, for any arbitrary n, as long as n can go low enough, which it can, nothing in this argument required n to be like 5 or something. And so we're okay. Okay. Hopefully that is okay. Okay. We have a sequence now, and I'm going to prove that if we want to define it recursively, that it's really just the same thing as defining it this way. So let's start with the base case. Okay, so base case is going to be right here. That tells us n equals 1 is the smallest it gets because that's the smallest sequence number we have. So A1 is equal to, and if n is 1, it's going to be 1 minus 1, plugging into here. That is equal to 0. Voila, it matched. Excellent. Next one. Inductive step. So that's going to be assume an equals n minus 1. And then what we want to do is show that n plus 1 is going to be equal to n plus 1 minus 1, which is just n. Okay, that's our goal. So we have an plus 1 is equal to, we are given this, that is how our sequence is defined right now. So let's go ahead and use him. Okay. So now what we want to do is, I know things about an. Oops. So let's substitute that in. And what I would like to do is make the same assumption for this guy, but I didn't assume that. So we're going to say, hold up. Let's do, let's use k. And k is going to be 1 all the way up to n. For k, assume, I'll say or n. Okay. Now I get to use this right here because it's true for all of them. And now if I do this simplification, these guys cancel. Excellent. So I got where I'm supposed to be. I am not going to put the box down saying that I've proved this yet. There's one more problem. This formula only works for n bigger than 2. So in order for like this to work, like if my n plus 1 were to be 2, and so if like n equals 1, I need to rely on 2 previous terms. I don't have 2 previous terms at that point. So what you have to end up doing in this case is you have to prove a second base step, or a base case. So then a2 is equal to, we plug in 2 right here, 2 minus 1, which is 1. So it's not like hard to do it. You just need to know that you need to do it. Otherwise, like, this formula is going to fall apart because you have P of 1 is true. You do not have P of 1 implies P of 2, but you do get that, like, P of 2 implies P of 3, right? Yeah. So without this connector, I knocked over my first domino, but he had no next domino to knock over. And so we have to say this guy got knocked down and this guy got knocked down. And then this guy is the one that's going to let us have the whole domino effect of everybody getting knocked over. Okay. So I'm going to show an example where like this can break apart if you aren't watching carefully what your argument depends on, like previously. Okay, I am going to prove that all ponies are the same color. Base case. We've got 1 pony, right? Because you can't have like -1 ponies or 0 ponies. If we've got 1 pony, it is the same color as itself. And then we have our inductive step. Assume groups of n ponies are the same color. Now we need to prove that a group of n plus 1 ponies will also all be the same color. So I've got a nice little drawing for you guys because I didn't want to have to draw ponies live. Here is our group. This is our n ponies. So that means we got to assume by assumption, they are the same color. Okay. How do we get our n plus 1 pony to be the same color? Well, the great thing about this is I said groups of n ponies. Like, it didn't say like this specific group. Just any group of n ponies has to be the same color. Which means, let's regroup them real quick. This is a group of n ponies. So that means I can assume that all these ponies have to be the same color. So here we go. This guy has to be blue. But then, like, we know that he's blue already. He was in our original group. So that means I have n plus 1 blue ponies. So they are all the same color. We've seen ponies. Like, my logic seems good, but we have seen ponies and they are not all the same color. Something has to be wrong. So the place that this went wrong was this regrouping step. It relied on something that's kind of hidden. Let's see. So if we clear away some of this stuff, let's look at a group of 2 ponies. So if I have a group of 2 ponies, then I would be like, okay, this guy is the same color of itself. This guy is the same color of itself. But when I try and do like a regrouping trick, I don't have like any ponies in my regroup. My entire previous group is gone. I have no ponies overlapping to adopt that color property from. And so my argument, relies on n being bigger than 2, which means I need a second base case to tie this in. But like, I can't prove that this is true for 2 ponies, which means the entire argument falls apart. So just like the sequence, I needed base case 1, I needed base case 2, because my argument was going to rely on more than one previous argument. Same thing here. I needed more than one previous argument, but I couldn't make all of those base case arguments, which means, in general, this isn't true. Okay. Hopefully I've made my point. As you're doing your induction proofs, make sure you're going back and double checking. It's like, did I need to make more assumptions? Did I need to do more base cases? Do I have all the information? Am I like inventing information that I'm not allowed to invent yet? Am I being careful? So you're just like, maybe at this point you're gonna kind of think and be like, well, why don't I just always assume all the previous cases are true? Like, well, now you're just like taking a canon to all the problems. I want you to prove that you know how to think about these problems. I want you to show me that you know when it's okay to just use the previous case and that's all your argument requires, versus you know when your argument is using more than just one little piece and you need to use strong induction now. Okay. So, just as a recap between induction and strong induction, induction is really great for like formulas that involve natural numbers. As soon as you start talking about real numbers, don't even try. It's not an induction problem. Strong induction is super good when you need like a recursive formula that's going to require more than one previous step instead of just the previous step. So like the sequence problem that we just did. Induction, it's great when you only need the previous step. And then strong induction again, when you have to do arbitrary divisions, that's another time when you want to use strong induction. So we did two of those problems, like we did breaking a chocolate bar up, and we did proving that you can write a composite number as the product of primes. We couldn't predict how we were going to break up that n plus 1. We were just like, it's composite, and so it's a times b. I don't know anything about a times b. So that would be an arbitrary division. They are very similar as how you go about it. They both start with a base case. You might need more than one base case. For strong induction though. And then step 2, you have an inductive step proving n plus 1. But again, for strong induction, you need all the previous results instead of just the nth one. So your assumption has to be bigger for strong induction. Okay, hopefully you can tell the difference between induction and strong induction at this point, because that's all I've got for you guys. See you next time.